All right, so I'll share the screen. Okay, so were you able to go through what we did last time in the class? What I'm basically mean to ask you is if you have any questions.
No, sir. Sir, I wrote a little bit, so I went through it. So can you share the complete notes, sir?
Oh, okay. So I'll share the notes with you as well. If you go on the website of Mega Lecture, there is this section notes, something called notes, right? If you open that, you can go down, scroll down a bit. You'll find a subsection of physics. In that, you'll see this link to Basel physics notes, something like that. So you can find most of the notes will be even shared over there, right? So I think they have started uploading the notes over there. Some notes that I am still preparing, they have also been shared over there. So you can always go and have a look at them. And but I think those notes are without these handwritings that we do in the class. So I'll share these notes as well over there. So you can always get the notes from there under the A2 section. So that's cool.
Yes, sir.
Okay, perfect. So any questions from what we covered in the last class?
Sir, we went over the gravitational field strength,
Yeah.
what is a field, and the formula of the force.
Yeah, so we discussed these things. So anything that you want to any question that you might have, any doubt that is everything clear? That's what I'm basically trying to ask from what we did in the last lecture. Is the concept of field clear to you? Is the concept of gravitational field clear to you as well?
Yes, sir. Sir, but the only thing that was not clear was why do we include the negative sign?
Oh, perfect. So, okay. So, I mean, not perfect that it was not clear. What I meant was, okay, so I got your point, right? So I'll just clear that to you. Okay. So, whenever you have, so for example, I have these two bodies, right? So here are two bodies and there is going to be an attractive force between these two bodies due to the gravitational field. Now, the radius vector comes directly outward. So from this body, it's coming outward in this direction, right? So the radius vector basically points outward from the bodies like this. But the, what do you call that? The force is inward, right? Because it's attractive force. So it's inward. So this is the force. So if now you have to define you have to pick a coordinate system where you can say that my right, if you say that right is positive, then left is immediately negative. So if my radius vector is in one direction, which is, let's say this is to the right, right? And F is in the other direction. So if my right side has a positive sign, then the left side would automatically have a negative sign. So that's why we have this negative symbol in the expression for force. Is that clear now?
Yes.
Okay, amazing. So, okay, so that's that. And we covered gravitational field strength. We wrote down, we discussed this expression for the gravitational field strength. So this expression is clear, right? It's basically from F equals ma. And if I compare it with the gmm by r squared, then this m is this m and everything else that is left is my a, but a is the acceleration due to gravity, so we call it g, and hence it is gm by r squared, right? So m is that mass which is the source of the field, which creates the field in space-time. M is that particular mass. So for example, it could be in our solar system, it's mainly the sun, which creates a gravitational field for all the other planets which will revolve or orbit the sun, right? And you can see that this gravitational field strength is independent of any other mass that is in the vicinity of this capital M, which is creating the gravitational field. So that's what we basically discussed in the last lecture. That's where I think we ended, or the last lecture basically ended at that point, if I'm not wrong. So we can then move on, and we have an example over here. Let's try to work this out. Can you see the screen properly? I mean, should I zoom in more, or is this okay?
This is okay, sir.
Okay, perfect. So now let's read this problem. It says, assuming that the Earth is a uniform sphere of radius this. So we're given a radius for the Earth, and we're just making an assumption of its geometrical shape as a sphere. And we are given the mass of the Earth as well. So this is the mass of the Earth. We are required to find the gravitational field strength G at a point on the surface. So if they're asking you to find the gravitational field strength on the surface, then the radius of the Earth is, the vector comes out from the center of the Earth and it reaches to the surface of the Earth. That's the radius vector. So that's your radius, which is given, that the radius of this Earth is given as 6.4 times 6 meters. So that's this radius. So it's the radius on this surface, right? So that's the surface of the Earth. So it's very simple. If you look at this expression, it's simply G is equal to Gm by R squared. All you have to do is plug in the values. So we'll use, so now we have ignored the negative sign over here. It's not really ignoring the negative sign. You can say, you can write down over here, right? So it's always nice to let the examiner know what sort of coordinate system that you're choosing. So in this problem, let's say, for example, we choose that downwards is positive and upwards is negative. So in that case, there will be no negative sign in this expression, right? Because we know that the gravity of the Earth, it would be attracting things down to the Earth. So downward, if downwards we have taken it to be positive, then we'll not put a negative sign over here.
Sir?
Right? Yeah.
Sir, I did not understand the examiner thing.
Oh, I was just telling you that it's always a nice idea to define a coordinate system for your problem. So what I mean by that is that you can just say that in your problem, what you're doing is I'm choosing my downward direction to be positive, and I'm choosing my upwards direction to be negative. So if I'm using this coordinate system, then there will be no negative sign in this expression for G, because acceleration of gravity is going to pull things down to the Earth, right? So if downward I've taken it positive, then I'll not include that negative sign over here. But suppose if you had done the other way around, if you have taken upwards as positive and downwards as negative, then there would be a negative sign over here. Is that clear?
Yes.
All right, cool. So now we just have to put in the values. This G is a constant that's given to you in your paper. That's, I think it has, let me make all of these things. Let me make them small, or let me move them around. 1 second. So that I have more space. Okay, let's just here. All right, okay. So this is 6.67 into 10 raised to power minus 11. And for now, let's just ignore the units. And this is G. Mass of the Earth is 6.0 into 10 raised to power 24. And we have radius. Now we'll use this radius. The value of radius will be exactly this, because this is the radius of the Earth. And I just explained that this radius is from the center of the Earth to the surface. And they're asking you to find the value of G on the surface, right? So you'll just put this value of radius in here, and the rest is just putting this in a calculator and getting 4.34 meters per second squared. So sorry, it is not 4.43. Yeah, and it should not even be 4.43. If you solve this in the calculator, it comes out to be 9.77. And that's something that you expect, right? Because we know we are very familiar with this thing, that the acceleration of gravity is around 9.8 meters per second square, right? So that's a very okay answer for the gravity on the surface. Now let's check what happens. The next part is at height 0.5 times the radius of above the Earth surface. So what they're telling you is that you have to they're asking you at the height 0. Actually, it should have been 1.5, right? This is a mistake in this example. It is 1.5, because 0.5 would mean that you are going inside the surface of the Earth, right? So you're digging in the surface of the Earth, because height is decreasing by half, right? So that's not what they're that's not supposed to be a question. The question is, it is 1.5 times the radius above. See, they have clearly mentioned it's above the Earth's surface. So it's 1.5 times above. So did you get what I'm trying to say? Did you get why did I say that this was a mistake in the question? Because 0.5 times the radius would make it half of radius. And half of this vector is somewhere over here, right? And if I use that, then that's not above the surface of the Earth. So there was this mistake in the question. It should be 1.5 times the radius above the Earth's surface. So what that means is, all I have to do here is multiply my radius of the Earth with 1.5, right? And then use all of this, put all of this in this R, right? So what I'm basically saying is that this would be G is equal to the 6.67 into 10 raised to power minus 11 into mass of the Earth is still 6.0 into 10 raised to power 24. But in place of the radius, they have said that we want to find it 1.5 times the radius of the Earth at that height. So we'll just multiply the radius with 1.5. So the radius was 6.4 into 10 raised to power 6 meters. And so the answer that you get from here, whatever the answer that you get, I'm not going to put all of this in the calculator, but so this is how you will go about the problem. So is that clear, or do you have any question?
No questions.
No question? Okay, perfect. So the next problem is the acceleration due to gravity at the Earth's surface is 9.8 meters per second squared. Calculate the acceleration due to gravity on a planet which has the same density. So the density is same, but the radius is 2 times. So twice the radius of the Earth. So I think we'll use next page, because I don't think we'll have enough space over here. Let me see. Can I get rid of this? No, I cannot. Okay, so okay, so let's get our information. Let's try doing it here. So the acceleration due to gravity on Earth's surface is 9.8 meters per second squared. We are required to calculate the density, the gravity acceleration due to gravity on a planet which has same density. So density of this planet is the same as density of the Earth. However, the radius of the planet is twice the radius of the Earth. So here we have some of the expressions. Now what we can do is, because what we can do is we can write down the expression for acceleration due to gravity, which was gm over r squared, right? Now let's try to find a ratio between the acceleration of gravity on this planet to the acceleration due to gravity on the Earth, right? So what that would do is that would basically get our answer in terms of the radiuses alone, because we don't know the mass, right, at this point. What we know is that the density is the same. So what we can do is, if the density is the same, then if I write it as a ratio, let me write it over here. So if I say gp over g Earth, right, is, so what is gp? Well, if you know that density is mass over volume. So in place of mass, what I can do is I can write density times volume. So that's mass. So I can replace the m in this equation. This m can be replaced with density times volume. So I can write G, density is rho, and it's the same. So they're saying that the density rho p is the same as rho e. So let's just say that it's just some constant rho, right? Because both values are same for planet and Earth, right? So what is volume? Spherical object. So the volume of a sphere is 4/3 pi r cube. Now this r is for the planet. Now the reason I'm using rp is because they have clearly specified that the radius is different, right? So it is twice the radius of the Earth. So this is my volume, and then you have divided by r. We'll have this thing r squared, right? And then divide all of this thing with g rho. And again, the volume is 4/3 pi. For Earth, we'll use radius of the Earth cube divided by r squared. So these r squared goes away. Remember this r, the one that I just canceled, they're not the radius, they're the distance between the two, right? So these will go away. No, it will not go away. Actually, let me just correct myself. G was defined as gm by r squared, right? So this r was the radius of the planet, right? So just ignore when I said that it's not the radius of the planet. It is the radius of the planet. So we'll put subscripts over here. So this was for planet and this is for the Earth. So if there are 2 of radius of planet over here, so they can cancel with that 3 and only 1 will be remaining. And similarly, these will go away and there will be only 1 remaining. And constants will go away. Rho is the same, so it will go away. G is the same, it will vanish. Pi will cancel, and you're left with Rp over Re. Now that's the ratio Gp over Ge. Now you can, we know that the radius of the planet is 2 times the radius of the Earth. So I can say 2, in place of Rp, I can put 2 times Re. And then we have divided by Re. So we get 2. So this means that the acceleration due to gravity, let me do it over here. The acceleration due to gravity of planet P will be 2 times the acceleration due to gravity of Earth. So it would be 2 times 9.8, which will be 19.6 meters per second squared. So that's what we wanted to compute. So is it clear?
No, sir.
Okay, so yes, you can ask me where is the problem. Is there any specific thing that you did not get?
Sir, the cancelling out.
Oh, okay. So I think I'll go to the next page and we'll do it a bit more neatly, this part, right? I think this is very congested. And so even I was having problems solving it over there. I think we'll use this well amount of space and let's do it over here. Okay. So you understand the point where we took the ratios, right? So we said GP over GE, where G are the acceleration due to gravities. With P, it's for the planet, and with E, it's for the Earth. Now, we know that GE is, or normally G is defined as GM by R squared. But the question gave you information about density. It says that the density is the same. So I need to get rid of this M and have a density factor over here. So I know that density is mass over volume. So mass is basically density times volume from this. So now I can write another expression for G in terms of density, which is G rho V divided by R squared, right? So now let's write this thing for the planet P. So we'll have G rho. Now what is V? Any planet or even Earth, we assume them to have a geometry of a sphere. So volume of sphere is 4 by 3 pi r, but this is for planet P. So we have rp squared. Then we have, rp cubed, right? It's the volume. And then we have this whole thing divided by, you can see over here, there's r squared. So you have rp squared. Now divide this whole thing because of this sign, right? This one, and put the value of GE. It is again G, density is the same. That was mentioned in the question. So we are just using rho. And then we have volume as 4 by 3 pi r. This time it is the radius of the Earth cube divided by radius of the Earth squared. Now you can see that this is a sign for dividing, right? So you can just you can cancel some quantities over here. See, look at this. What happens here is that you have 3 rp upstairs and you have 2 rp downstairs. So these two will go with this, right? So we'll only be left with 1 rp. This is clear, right?
Sir?
Yeah.
Sir, which of the radiuses was twice?
Okay, so they told you that rp is 2 times re. So they mentioned that the radius of the planet is twice the radius of the Earth. If I go back over here, you can see they said, but twice the radius of the Earth, right? So on a planet which has same density, but twice the radius of the Earth. All right?
Yes, sir.
Okay, perfect. So this cancellation is clear, right? So you can get rid of this 2 rp squared and you can get rid of this 3. Similarly, over here, you can get rid of this and you can get rid of this 3 from here. So only 1 re is left. So this becomes G rho 4 by 3 pi rp divided by this, divided by G rho 4 by 3 pi re. So G cancels, rho cancels, 4 by 3 cancels, pi cancels, and you're left with rp over re. But rp is 2 times re, so you are left with this thing. So this cancels and you're left with 2. This means that the acceleration due to gravity on the planet is 2 times the acceleration due to gravity on Earth, which is 2 times 9.81, and you get the answer, which is 19.6 meters per second squared. So now is it okay?
Yes, sir.
If you still have any question, you can ask. No problem.
No, sir, I only had the issues in the cancellations.
In the cancellations, right? Okay. So now you got it, right?
Yes, sir.
Okay, perfect. So, okay, so the next thing is, let's talk about okay, so now assume that Earth is a uniform sphere. That's how we assume the geometry of our Earth, right? And say it has a mass m. Now, the magnitude of the gravitational force from the Earth on the particle of mass m, which is outside the Earth, say it's a distance r away from the center of the Earth, you know that this expression for force is valid, right? So, yeah, did you understand what this statement means? It's just basically describing when this force, the expression for this force.
Yes, sir. I got it.
Right? So now, as soon as you release the particle, it will start falling towards the center of the Earth. That's what happens, right? So if anything that you release from your hand, for example, it falls to the ground. So it's actually falling to the center of the Earth. Because of that, there is some acceleration of gravity. And so that's the only thing that this topic was aimed to explain to you, which I'm pretty sure that you already have an idea of from the previous topic that we discussed in detail. So it's just saying that this thing that I wrote before as well, that F is equal to ma, but the gravitational force is equal to gm m by r squared. Now, if you compare these two, m goes with this m, and you're left with a is this thing. So you say a is gm by r squared, which is just you define another unit or another symbol for this, you call it g, because this is due to gravity, right? So that was this. Now, this acceleration is purely due to gravity, because the only force that we were considering was the force of gravity. So anything that falls freely on towards the surface of the Earth experiences this gravity. All right. So that's clear, right? I'll assume that it's clear because we talked about this previously as well.
Yes, sir.
All right, good. So next we have an example which says that you have a ship which is at rest on the Earth's equator. Assume that the Earth to be a perfect sphere of radius r, and the acceleration due to gravity at the poles is g naught. So g with this little zero over here. Then you're asked to express the apparent weight in newtons of the body of mass m in terms of m, g naught, r, and t, where t is the period of the Earth's rotation about its axis. So apparent weight is basically the weight which appears at equator, right? Because, okay, so what happens is at the equator and at the poles, the acceleration of gravity varies because the distance from the center of the Earth is the distance basically is different, right? So at the poles, you have more high, the distance increases, and hence the force of gravity will decrease. But at the equator, the distance is fixed, which is the radius of the Earth, and so the force of gravity increases.
Can you
So
explain it one more time?
Sorry, can you repeat?
Can you explain it one more time, sir?
Oh, right. Yeah. So basically, the idea of apparent weight is that the acceleration of gravity varies according to height, right? Because if you look at this expression over here, so for different values of r, the value of the g would vary. So at different heights or at different distances, g will have different values. So maybe at one, you're standing somewhere on the Earth, let's say you're on this extreme end, the value of G would be different compared to if you were on this part of the Earth. For this is the reason, by the way, that if you consider yourself standing on the surface of the Earth, the part, your legs are more closer to the Earth compared to your head, right? And so the force of gravity experienced by your legs is less compared to the force, sorry, it's more compared to the force of gravity experienced by your head. Do you get that? Because G is Gm by R, or you can write it in terms of F, which is Gmm by R squared. So if I increase R, then force decreases, right? So this distance is, say, R, some R, and the distance to your head is some R prime. So very slightly, the force of gravity is different on your head compared to your legs. So
Yes, sir.
that's,
I get
so
it.
yeah, so okay, amazing. So now we'll work out this this problem. So they're asking you to express the apparent weight when the body is at equator, right? A ship, the body is basically a ship which is at the on the Earth's equator. So well, they have, let's see, what else do we have over here? We have at the poles, the gravity is given as G naught. So let's see at poles, what happens at pole? So at the pole, we have F is equal to G ME M by R squared, where this ME is just the mass of the Earth, right? Because we are talking about Earth's equator. Now, this thing is simply mass times forces, mass times acceleration, but acceleration at the pole is G0. So we'll put this equal to G0. Now what happens at the equator? At the equator, there is the force on the ship. Let me try to draw it. So this is the equator. So now let's say that this black dot that I drew, that's the ship and it's at rest. Now force on the ship by the Earth is actually the normal force, right? So how do I draw this? So suppose that this is, okay, it's very hard for me to draw. Can you try to imagine that if you had a ship on this point equator, then the force of gravity that it would experience would be normal, which means it would be perpendicular to its surface because it's coming from the center of the Earth, right? It's directed towards the center of the Earth. Can you picture that in your mind, or let me try to think of something I can draw. Okay, so you can assume that this is the surface of the Earth. You can say this is at the equator, and there is a ship. So there is this ship over here, right? And so the force of gravity that it will experience would be the normal force, right? It would be this force, normal to the ship. So I think this makes it clear, right? This force of gravity is actually also known as the weight.
Yes.
So at equator, the force on the ship by the Earth is this normal force N. So this is the weight. This is the force on the Earth by the ship. The opposite of that is this normal force, which is the force on the ship that the Earth is exerting on it, right? In this direction. So do you understand that point as well?
Yes, sir.
Okay, perfect. So this would be equal to, now this, what should this be equal to? It should be equal to this mg, right? That's obvious. So that only in that scenario would this ship be at rest, if there is no net force acting on it, right? So it should be equal to the weight. That's a must. So to balance this ship. But remember, we're talking about gravity, and gravity is something that is keeping things in orbit around the Earth. So the Earth is spherical. So it's something like a circle, but in 3 dimensions, right? So that's a sphere. So something is keeping it in that circular motion. Something is keeping this ship in the circular motion. So that force is the centripetal force, right? And so the centripetal force is towards this thing. So we would have minus m v squared over r, or we'll use let's write it mv squared over r. Did you get this point? Why did I use this centripetal force?
Yes, sir, because it is the reactionary force.
Okay, perfect. Amazing. So now see that they asked you to express the weight n of your body of mass m in terms of m, g naught, r, and t. So how can I write time period from this? I need this velocity in terms of angular velocity. So instead of using this expression, I can use mr omega squared, because I know omega can be written in terms of time period as 2 pi by t, right? So you're familiar with this expression now. We looked at it when we were doing circular motion as well. Right? So n is basically the weight m equal to the weight mg minus mr 4 pi squared by t squared, right? So I just squared this thing. So this is what they were asking you to derive. Is it clear? Or do you have any question whatsoever? You can feel free to ask. Any question in understanding what happened
Sir, why
in
was
this
the
problem?
omega squared?
Oh, okay. So basically, centripetal force is mv squared over r. You can write it as this, but we need it in terms of angular velocity because we need time period, right? So in question, they have asked you t, the period of the satellite. So we have to write it in terms of time period. I cannot find time. I cannot write it using v in terms of time period. Time period is involved with rotations or oscillations. So omega is something that includes time period because I know omega is 2 pi by t. So I wrote this expression like this, and you can also do it. You can also go from this one to this by using this relation that v is r times omega. So put that v in place of this, and then you can write mr omega squared. And so then we just replace the value of omega with 2 pi by t, but omega was squared. So we got 2 squared is 4, pi squared by t squared. So is that clear now?
Yes, sir.
Okay, perfect. So can you tell me how much time is remaining in this meeting?
Less than 1 minute, sir.
Less than 1 minute. Okay, I think the problems took some time, and I was also a bit tired today. I think that's why we went a bit slow. But by tomorrow we'll finish this chapter and we'll do some problems. We'll include both problems from circular motion